Hello, dear students. Myself, Dr. Uttara Chandrawat from the Department of Chemistry, Government College, Kota. I welcome you all in this class on the topic hard and soft acids and bases. So, in the previous lecture, we learnt about the Pearson hard and soft acid base principle. He suggested a simple rule sometimes called Pearson principle for predicting the relative stability of the complexes formed between acids and bases, which was that hard acids prefer to bind to the hard bases and soft acids prefer to bind to the soft bases. It should be noted here that this statement is not an explanation or a theory, but a simple rule of thumb which enables the users to predict qualitatively the relative stability of acid-base adducts. So, now we come to the explanation of hard and soft acid-base theory and hard soft interaction. So, we should keep in mind, as I already told you, that a Lewis acid is an acceptor of electron pair and a Lewis base is a donor of electron pair. So, in the hard acid, the acceptor atom is characterized by these qualities. That is, it should be small, it has low polarizability, high electronegativity, and high charge density. While in the case of hard bases, the donor atom is small, it has low polarizability, high electronegativity, and high charge density. While in the soft acids, the acceptor atom is large, it has high polarizability, low electronegativity, and low charge density. While in the case of soft base, the donor atom is characterized by that these qualities, that it should be large, it has high polarizability, low electronegativity, and low charge density. So the key point here is charge and size and charge density. In the term of size, we notice that the atom of hard acids and bases tends to be small, whilst the atom of soft acids and bases tends to be large. Usually, this correlates to hard species being from the earlier rows of the periodic table, example oxygen, fluorine, chlorine, whilst the soft species being from the later rows, that is sulfur, iodine, phosphorus, etc. So if an atom, be it an acceptor or a donor atom, is large and is not highly charged, that means the atom has low charge density and therefore is soft. For example, iodide and silver plus. And if an atom is small and is highly charged, that means the atom has high charge density and therefore it is hard. For example, fluoride and lithium plus. There are also some species in between hard and soft which are called borderline species. For example, bromide and Fe plus 2. So now we know the definition of hard and soft acid base. Here is the core of hard and soft acid base theory, that hard acids tend to react with the hard bases and soft acids tend to react with the soft bases. The hard-hard interaction is governed primarily by electrostatic attraction between the positively charged acids and the negatively charged bases. The soft-soft interaction is governed primarily by the mixim or the overlap of orbitals between the lowest unoccupied molecular orbital of the acids and the highest occupied molecular orbital of the bases. Keep in mind that the hard and soft interaction is preferable but is not necessarily the only possible interaction. Hard-soft interaction is also possible when it is influenced by some external factors, which is why the theory says tend to react. For example, Soft silver preferably reacts with soft iodide ion to form silver iodide, and hard lithium plus with preferably reacts with hard fluoride ion to form lithium fluoride. However, there are also some circumstances where silver fluoride and lithium iodide are formed. So now we come to the classification of acids and bases as hard and soft. You can see on the screen the reaction AHB1, that is the adduct of hard acid, and B1 is soft acid, and B2 is harder acid. So AH, the adduct of AHB1 plus AS, that is soft acid, plus B2 will give you AHB2 plus AS plus B1. So from this double displacement reaction, it may be stated that B1 is softer than B2 when K1 is greater than 1. So on this basis, a list of hard and soft acids and bases may be obtained. Now you should know that this classification is not rigid, and there occurs a gradation from hard acids to soft acids and hard bases to soft bases, including the borderline species. The criterion of hardness or softness is ascribed to the hardness of the electron cloud associated with a particular species. A firmly held electron cloud having low polarizability makes the species hard, while an easily polarizable electron cloud characterizes the species as soft. The third category with intermediate characters will be a borderline species. So the details of distinguishing features of hard and soft acids and bases are summarized in the table shown here. So now we have the classification of fluids, acids and bases. On the extreme left hand side of the screen, you can see the hard acids. In this category, we have proton, lithium plus, sodium plus, potassium plus, beryllium plus 2, magnesium plus 2, calcium plus 2, etc. And on the extreme right of the screen, you can see the soft acids like cuprous ion, silver plus, Au plus, etc. And we have metal atoms and bulk metal atoms in this category. Borderline species, in this category you have Fe plus 2, cobalt plus 2, nickel plus 2, sulfur dioxide, etc. Now we come to the features. So in the hard acids, acceptor atoms are marked by small size, high positive oxidation state, absence of any outer electrons which are easily excited to higher states. Fourth feature is absence of d electrons. Fifth is they are usually lighter metal ions. And sixth is that they are known as Lewis acids, which are not polarizable and prefer to coordinate with hard bases. While the soft acids are characterized by where the acceptor atoms are marked by large size, zero or low positive oxidation state, presence of several excitable valence shell electrons. Fourth feature is they have nearly full d electrons. Usually they are heavy metal ions, and they are termed as Lewis acids, which are polarizable and they prefer to coordinate with soft bases. So now we come to the bases. In the category of hard bases, we have ligands such as fluoride, hydroxyl ion, water, amine, carbonate, nitrate, etc. And in the softer category of bases, we have hydride ion, amine, cyanide, carbonyls, iodide, etc., thioethers, phosphine. And when we look at the features of the donor atom, you can see on the screen that the donor atom has in the hard bases, it has high electronegativity, low polarizability. It shows the presence of filled orbitals. These are anions, usually they are anions or neutral molecules. which are known as Lewis acids or Lewis bases or ligands, which prefer to coordinate with hard acids. And in the softer category of bases, the donor atom is marked by low electronegativity, high polarizability, it has partially filled orbitals, and usually they are anions or neutral molecules called similarly as Lewis bases or ligands, which prefer to bind with soft acids. So from this table, it is clear that there is no line of demarcation between the hard and soft species. Within each group, there exists no equal hardness or softness strictly. For example, alkali metal ions, they all are hard, but within the group, hardness decreases. That's why you see lithium is the hardest, while cesium plus is softer, as it is larger and more polarizable as compared to lithium ion, which is on the top of the group. Similarly, looking at the ligands, we see that nitrogen is a hard base. And we see in ammonia being of smaller size, and if the polarizable substituents are present, it will turn to be sufficiently softer. In case of pyridine, you can see the polarizable substituents are present. So further, we may use the terms such as a moderately weak and fairly soft, very hard but weak, by considering the strengths of acids and bases. So with this we complete the classification of hard and soft acids and bases. The rest of the topics will be covered in the coming lectures. Till then, goodbye.